Hello, everybody. My name is Maciej Brodecki, and I'm from Sygnis SA, a Polish deep tech company, organizer of these webinars. And I am welcoming you to the 6th edition of Knowledge Has Layers webinars. Today with me is Grzegorz Kaszyński, Vice President in Sygnis, and Xuan Huan Lim, the researcher and InssTek. We will wait just 2 minutes for another attendees that may be late, and we will start the presentation right away. Okay, I think it's time to start the presentation. Few information about Sygnis. Grzegorz, the stage is yours.
Hello, my name is Gregory. I will tell you just shortly about what is Sygnis. Sygnis Spółka Akcyjna is a Polish company. We are based in Warsaw, and we are a team right now, more than 70 people, engineers, scientists, designers, and we work in Poland. This is our main area of operations. We are based in Warsaw. We started in Warsaw University, but we grew to several different places. You can visit us in Warsaw Cambridge Innovation Center to talk about prototyping and new technologies. And we are growing fast. We have been last year, at 48th place in Deloitte Technology Fast 50 Central Europe. And our main job is to promote rapid prototyping, new technologies. We are in a lot of webinars, applications, and materials. We have our own production facilities. We have our own research team and development team. And what is really important, we are not your standard sales company. Our backbone is research and development. We have different projects ranging from biotech to engineering to special materials around mostly rapid prototyping. In total, we have more than 20 million zloty in fast-track projects currently running in our company. And what we are doing, we have our 3 main areas that are divided between Sygnis Biotechnologies, Sygnis New Technologies, and Sygnis Nanotechnologies. But what is really important for us is that it is a one company. People are working together and exchange ideas and helping each other. So we can use industrial applications from Sygnis New Technologies into Sygnis Biotechnologies and help our users in biology with solutions that we devised for industrial customers. In biotech, we focus on 3D bioprinting. As I said, the core for us is additive technologies, microscopy, 3D tissue models, and omics. In nanotechnology, we go for ultra-high vacuum and nano fabrication with Femtica. Again, not only subtractive, but mostly additive technologies and solutions going down to hundreds of nanometers. And the main focus of the company, Sygnis New Technologies, is rapid prototyping and 3D design and engineering. We are working with several different technologies. So our pride and our national company, Sinterit, we are working with SLS techniques. And we are working also with a new player on the market, so Mimaki. We can print engineering devices with Sinterit. We can print full color systems. This, what you can see on the screen, is from the printer. It is not painted. We are working also with resin printers in different applications, from customer versions to highly sophisticated industrial solutions from DWS. We are focusing on FDM from industrial applications, special materials, up to For example, this is a very good example of cooperation up to printing implants. So this is between industrial applications and biotech applications, but we are also working with customers to 3D print, directly 3D print implants with peak materials. Also, of course, we are working with metals, and in this area we are working with Aconity and InssTek. And from InssTek you will hear about their amazing technologies in a second. And of course, we are focusing on rapid prototyping and low volume, low scale production. So we have our own machines, our own designers, so we can prototype, produce, and help you with all techniques. Anything can be rapid prototype or 3D printed, we get it covered. So please feel free to contact us and talk about even the craziest ideas if you want to use 3D printing. In this case, thank you, and let me invite our colleague to the stage.
For greeting. Good afternoon, everyone. I'm Seung-Hwan Lim from InssTek. I'm an additive manufacturing researcher in InssTek R&D Center. Before we started, thank you to the Sygnis team for giving me a great opportunity. Today's topic is multi-material manufacturing. With technological advances, there's a growing demand to use materials in various ways and combinations. I would like to talk about the whole process of applying multi-material manufacturing to industrial environment, from material research to practical applications. As you can see, I've divided my presentation into 5 parts. First 2 parts are about DED technology, which is one of the 3D printing technologies, and how it can be applied to material research. And later 3 parts will focus on processes that we need to apply this research to actual industry. After that, we will cover examples of multi-material manufacturing applications for each industry. Before we get into it, let me introduce our company, InssTek. InssTek was incorporated in 2001 and specialized in metal 3D printing business using DED method. We are a technology-based company and have our own technologies in various fields, from hardware to software, such as powder feeding, optic design, and 5-axis CAM. We are based on middle area of South Korea with 45 employees. We specialize in manufacturing AM machines and AM service, such as printing, coating, cladding, and repairing. We are working with many global partners and customers in Europe, America, and Asia. First, I will introduce DED technology, which is one of the 3D printing methods. After that, we will look at the many advantages of DED technology. DED stands for direct energy deposition and is a 3D printing method that uses an energy source to make a pool of molten metal. To this molten metal pool, feedstocks are supplied and solidified as a one part. DED technology can be classified according to the type of energy source and feedstock. Metal feedstocks are used in forms of powder or wire, and as energy sources, laser beam, electron beam, plasma, arc, sometimes kinetic energies are available. So there are many companies serve DED technology with various combinations of feedstocks and energy sources. Among them, InssTek uses combination of metal powder and laser beam. As you can see the picture in the left side, laser and powder is focused to one point through the nozzle, and there are two vision systems is watching the metal and control the process parameter to better quality. Besides the ED method, there are many different metal 3D printing systems. As you all know, powder bed fusions, binder jetting, material extrusions are representative ones. To briefly summarize, powder bed fusion is a method that applies heat sources to particles contained within a powder bed, which gradually indexes down as each layer is completed and new powder is spread over the build areas. Binder jetting is similar with powder bed fusion. It uses thin layer of powder, but it uses special material called binder to bind the powder. After binding the parts, they do sintering to be a metal. Metal extrusion method melts wire-shaped metal with heat and solidify to make shapes. Metal 3D printing can be delivered in various ways like this, so it is important to understand characteristics of each processes. By this understanding, user can make good use of it. Today, we will focus on DED methods, advantages, and possible applications. DED has many advantages differentiated from other methods. I will talk about four main advantages: scalability, add-up, mechanical properties, and multi-material. First one is scalability. Unlike powder bed fusion and binder jet methods, DED method doesn't need powder layer. It has a movable printing module that applies material and energy sources to target point. Thus, its printing volume can be expanded to comparatively large size. And also, if you use larger beam size, printing speed is dramatically increased. Large beam size can contribute to this scalability. Also, DED method and robot arms are a good match. Robot arms can control the motion of printing module with high degree of freedom and wide working range. This feature is especially competitive in industries that need large-sized parts. Of course, if you use multiple robot arms, productivity can be increased. Second advantage is add-up. For many 3D printing methods that use metal powder layer, it is general to start printing with empty space to make qualitative layer. On the other hand, DED method has few restrictions on substrate status and is capable of adding up on existing part as well as making new part. Thus, DED is suitable for various processes such as repairing, remodeling, coating, and cladding. Since it can be used with other manufacturing processes, metal manufacturing processes that were previously impossible can be done. Third advantage is mechanical properties. I've heard that some question about the applicability of 3D printed metal part to real industry. But many research has shown that the mechanical properties of the results produced by the DED method are similar to those of the existing manufacturing methods such as casting and forging. And some of them show better results depending on the material. These features are about some defects. During printing, process parameters should be controlled precisely not to damage mechanical property or generate cracks and defects. If process parameter is not optimized, defects like features can be occurred. InssTek has standard process parameter for more than 20 types of materials that are most common in industry, such as iron, nickel, and titanium. When working as a standard process, the internal density is very excellent at 99.8% or more. InssTek has a standard process recipes of more than 20 types of alloys shown in the table. Various alloys such as titanium, steel, nickel, copper, and cobalt are available. I brought an example for comparison. These tables are mechanical properties of stainless steel 316L fabricated with various methods. The cases values are similar or better than those of existing methods, and also they can be improved through subsequent processes such as heat treatment. Last feature is multi-material. Since the process is performed continuously supplying metal powder to the molten pool, if the metal powder is changed during supply, several different materials can be stacked partially in one process. With this feature, multi-materials can be used in various ways, such as bonding of dissimilar materials or gradient materials. It is DED method's own advantage that it is not available with other 3D printing methods. It is impossible to control the composition of the material in shape of wire or powder layer. In this way, new type of materials can be manufactured. The sample in this picture is an example of a gradient material. It is composed of R-bronze, which is copper-based alloy, and T800, which is cobalt-based alloy. R-bronze has yellow color, so that we can see the content of R-bronze is changing gradually as the gradient color changing. It is impossible to make these kinds of materials with the existing process. Using the multi-material will have a lot of importance in future industry. InssTek is developing leading technology in the field with Ded Technology. In this chapter, we will cover new material research method. The new method operates with Ded Technology, which have strong potential in multi-material handling. Conventional material research method is too long and many steps to make one specimen. Researchers follow the long steps to make a molten alloys with design composition. After cooling the molten metals, they machining and analyzing the specimen. But if you make a specimen with a new method, it's very simple. Just 3D printing, machining, and analyzing. Comparing two methods, new method is simple, fast, and easy to test various compositions. Thus, it is possible to restart the experiment quickly when tests fail. And if you make a specimen with 3D printer, it is a safe process due to the closed environment. I think many of you guys are unfamiliar with this new method. For your understanding, I prepared some research papers tested with Ded Technology. Let's study it together. This paper is written by Professor Yachao Wang from North Dakota University. This paper is for evaluation the in-Situ alloys effectiveness. In this study, samples made of inconel alloys were compared with samples made of in-Situ alloys nickel, chrome, molybdenum, niobium, iron pure element powder, which is prepared with same composition as inconel alloy. Finally, they found that it shows similar mechanical properties in two samples, which means in-Situ alloying can be a new alloy research method. The second paper is written by KAIST and InssTek. This research was developing a new high-entropy alloy with nickel, cobalt, molybdenum, titanium, and aluminum. By software simulation, target compositions were designed. Each 5 pure element powder were supplied in powder feeder independently. After that, test was conducted with changing compositions while 3D printing. As in the picture, 9 different composition samples was made by one click. In one sample from the 9 samples, stable gamma prime phase was discovered. This new material was applied for a patent. The paper is written from Russian University's Caltech. This research was about functionally gradient material. FGM is a new alloy by mixing 2 different materials with gradual composition changing. iron bronze and stainless steel 316 was used for research. These two materials are non-magnetic powder, but FGM produced from two materials shows soft magnetic properties. Changing materials composition layer by layer is impossible to make with conventional method. DED is the only method to make this type of material. The fourth paper is probably an unfamiliar form of study. This study is related to the DED manufacturing processes. Machine learning was conducted by combining the resulting data and various process parameters. This is a study to find optimal process parameters by predicting process quality through machine learning. It is a study that utilizes the fact that the experiments can be quickly conducted under various conditions. In this way, a new field of research was created by linking software technology and material research. In addition, InssTek verified multi-material related papers such as high entropy alloys, metal matrix composite, functionally gradient material into the MXLab system, and confirmed that the material research methodology using DED could replace the conventional method. You can download more than 15 case studies in our website. All of the previously introduced research were conducted with InssTek's DED system. As a result, various types of studies such as in-Situ alloying, high entropy alloy, functionally gradient material, and machine learning have been created by taking advantage of being able to experiment quickly under various conditions. Then now, I will explain how to construct an experimental environment for material research using DED. When building a research environment using DED technology, three major technologies are key: power supply technology, optic module, and software. The first core technology is powder supply technology. In powder supply technology, key factors are how precisely powder can be supplied, how small amounts of powder can be supplied, and how various powders can be supplied at once using multiple feeders. The second core technology is the optic module. Using an industrial purpose optic module, high power lasers are used and specimens become bulky. Therefore, an optic module made in a size suitable for the research environment is needed. Additionally, a manifold monitoring system will support the collection of experimental data. The third core technology is software. In general, several softwares must be used to handle metal 3D printers. 3D modeling of specimen is produced with software called CAD, and the CAD program calculates and simulates the path through which the machine moves. All of them are softwares that require studying hard because their functions are complicated. Therefore, there is a need for a software that can simplify design specimens and form alloys. Based on three core technologies, by combining the moving stage and laser systems, research environment with DED technology can be established. However, InssTek launched all-in-one material research machine, which includes these 5 components. I will briefly introduce this innovative machine, MXLab. MXLab is world's first material research machine with hexapeder. The machine includes 500-watt laser, 6 powder feeders, optic modules, and mechanical stages inside. Powder feeders are operating like this animation. By changing the speed of feeder, amount of supplied powder is changed. If you want to supply multiple powder in at once, multiple feeders will be operating, and each feeder can be controlled independently. Thus, various compositions of powders can be mixed while 3D printing and become an alloy. As I explained before, Accurate control and minimum quantity control is important for material research. Powder Peter in MX Lab shows excellent capabilities for two criteria. As shown in the graph at the bottom, powder is stably supplied more than 7 hours. Also, very little amount of powder, 0.03 gram per minute based on TI64, can be supplied. Also, with hexapeter, multiple pure element powder can be supplied with independent feeding lane. Thus, researcher can do in-Situ alloying or live alloying like a right-side graphic. Next feature is optic module. Optic module includes optic cartridge, nozzles, and vision systems for multiple monitoring. MX Lab's optic module can generate 400 micrometer beam diameter. This size is efficient size to conduct material research. With this size of beam, 10 millimeter cubic samples can be made in 30 minutes. Maximum printing volume of MX Lab is 150 millimeter cubic, and many data can be collected with multiple monitoring systems. Also, there is special software named Material Designer to support designing specimen. With this software, researchers just select specimen shape, size, compositions by layer, and process parameters to design a specimen. They don't need to study other software like CAD and CAM to handle 3D printer. There are more functions to support research. AutoJet is for maintaining the heat input. It controls the gap of specimen and nozzle constantly. Next, researchers can change the laser power easily, thus they can experiment various conditions. Also in the system, it is easy to extract many data made and collected during process. Researchers can use this data for their analysis. In this chapter, we will experience material research using MX Lab together. The material research process using MX Lab is as follows. Design the specimen with the composition to be experimented with in the software named Material Designer. Set the metal powder to be used for the equipment and proceed 3D printing. After that, analyze the specimen. This is the whole process for one experiment, and this process can be done in an hour. Now, I will show the entire process through the video. The video to be played can also be found on InssTek's YouTube. The video is about researching high entropy alloy by changing composition of powder. You can see in the video, 5 feeders are independently working. As you can see in the picture, 5 elements are very well mixed. Now you can understand how powerful material research using DED is. In this chapter, we will look at how multi-materials are applied to the actual industrial sector by case studies. I will introduce 6 industries: aerospace, heavy industry, automotive, manufacturing, medical, and semiconductor. These are all success stories that InssTek has collaborating with its customers. First industry is aerospace. InssTek did lots of projects in aerospace field. These 3 cases are representative case. We manufacture rocket nozzle with multi-materials, and we did repairing compressor blade and jet engine air seal. I will explain more about rocket nozzle project. The shape and size of rocket nozzle is actual scale for real use. And inside of rocket nozzle, cooling channel for thermal control exists. We use 3 different materials in this project. We used nickel-based alloy, Nimonic 75 and Inconel 718, and copper-based alloy, bronze. This video is about how we make rocket nozzle. This big size of rocket nozzle in 180 hours. Second industry is heavy industry. In this field, we did multi-material valve manufacturing and shaft bush bearing cladding. Multi-material valve is made by combining 3 parts: valve bore, valve body, and cap end. And the valve can be separated in 2 regions. As you can see the graphic in bottom left, there are 2 color regions, red and gray. The red region is vulnerable to corrosion due to direct contact with seawater. So we made with Inconel alloy for red region, which have high corrosion resistance. Outer gray region is made with stainless steel, which is easy to machining. This project was proceeded with consortium by 7 companies. Finally, we received certification from Norwegian certification company, DNVGL. This video is about how we manufacture multi-material valve. InssTek conducts simulation on its own CAM software to verify the possibility of collision and then proceed with 3D printing. This video is about cladding on bush shaft bearing. We cladded with white metal on carbon steel base. You can see the whole process is doing by automatically. Third industry is automotive. In this field, we did cladding on automotive engine and repairing molds for automotive parts. In case of valve seat cladding in automotive engine, copper-based alloy was cladded on a base made of aluminum. As a result, we improved fuel efficiency by about 2% to an absolute number. This video is about how we do cladding on valve seat in automotive engine parts. next industry is general manufacturing. In this field, we did manufacturing gas turbine blades and multi-material disc parts. In these disc-type parts, three materials were used for cooling channels. Iron-based alloy and copper-based alloy was used. Industry is medical. We adapted our multi-material DED technology to artificial joints. There are three types of artificial joints. Cup component is for the hip system, and tibial component, femoral component is for the knee systems. Porous coating technology is a technology that makes the smooth surface of the artificial joint too rough. We do porous coating with pure titanium powder, which is biocompatible material. With this material, bone is growing inside of the coated surface. Thus, we don't need chemical bonds to attaching bone and artificial joints. This technology is in clinical trial stage, and more than hundreds of cases are now testing. And there is knee implant called femoral, which is made with cobalt chrome. InssTek succeeded bonding pure titanium on cobalt chrome by world first. This video is about how we do porous coating on artificial joints. Porous coating technology can be used in semiconductor industry. Pictures in left side is deposition ring, which is core part in semiconductor producing machine. During semiconductor producing process, ions can be popped into vapor, and this causes defects to vapor. Traditionally, arc coating was used in deposition ring, but our porous coating shows more good bonding properties. Now, our customer testing this porous coated deposition ring in real processes. As you can see in previous chapter, multi-material is already widely used in real field. Now, I will conclude this seminar with summaries. Expansion into space, development of the energy industry, and dissemination of artificial joints. As technology advances, the demand of parts used in extreme environments will gradually increase. Materials used in extreme environments are difficult to manufacture with existing metal manufacturing processes. And there will be many new alloys to be studied according to the field's requirement. In the future, the world will need new alloys and new combination of materials to overcome the extreme environment. Thus, we think multi-material manufacturing will be an important keyword. Successful multi-material manufacturing, material research, and industrial application must be closer and move as a one process. It works for expanding multi-material manufacturing. So we made a machine for material research MX Lab and industrial machine MX Fab and MX Med. After all, material research is DED. Researchers try to make materials with suitable properties for industrial applications. DED is the only method to material research with changing the alloy composition. InssTek wants to pioneer this field with material research experts in here. Finally, I will end the presentation by showing a brief teaser video. Teaser video is the future plan of the InssTek. InssTek wanted to stably manufacture such super large outputs based on material research. Thank you for listening. If you have a question, feel free to ask me.
Thank you, Lim, very much for your presentation. It was really compact with the information about the technology. And I think it will cover most of the questions, but we have one right now, and I am inviting the attendees to ask questions in the Q&A section. We will talk about them right now. So the question is, what is the maximum deposition rate with HEAs with InssTek machines?
Actually, for the high entropy alloys, if you wanted to use the high entropy alloys for the manufacture, I suggest using a pre-alloyed high entropy alloys, because the pure elemental powder is expensive than premixed alloy. And for the deposition rate, now we have a maximum 2,400 micrometers beam size. So we can build up maybe I think I must do some calculations, so I will answer this question a little bit later. Sorry.
No problem. If you have any questions, you can also write to us and write to Lim himself. I think, Lim, you will answer the questions later if it's too complicated. But we have another questions. Is it possible to process CU powder with InssTek machine?
Yeah. For the copper, we can print a copper-based alloy like R-bronze. And if you want to use a pure copper, now we can do just a layer, 1 or 2 layers, because we are now researching level, and maybe we can do pure copper this year or next year.
Perfect. Another question, is it possible to mix anorganic powder, MOS2, with metallic powder, like CUSN?
For technically, we can supply these 2 types of powder if the powder shape is spherical. But actually, we did not try an organic powder molybdenum S2, so we must check it later. And for the first questions, we can deposit 66 cubics in an hour. Okay.
Perfect. So another question is, what are the requirements for the powder to be used in the MX lab when it comes to particle size and shape?
Yeah. For the particle size, we suggest 45 micrometers to the 150 micrometers. And for the shape, we use spherical powder.
Thank you. And another question, what are the biggest challenges you faced while depositing multi-material parts?
Okay. I think the most biggest challenge was there are too many material combinations. So if we try, sometimes we cannot predict before we printing. Sometimes they made another alloying, and sometimes they be cracked. So it is hard to predict multi-material deposition before 3D printing. Maybe that is the biggest challenging point.
Thank you. And another question, what is the recommended particle size?
Maybe I answered before. We use 45 micrometer to the 150 micrometer powder.
Perfect. And another question, and I will like to invite any other questions also. Can you add rotational axis, which would allow me to make coating shaft?
Of course, you can see that some applications in the later parts. Our machine is simultaneously 5 axes. We have an XYZ axis and turning A-axis and C-axis. So you can use coding. You can use this technology to the coding shop, of course. But MS Lab is for the material research machine. So the MS Lab is just a 3-axis machine.
Thank you, Lim. I didn't see any other questions, so we will be going to finish the webinar. Oh, the last question just occurred. So how can we simulate multi-material DED process, especially at the interface of the two materials? And can you also comment on defects, pores and cracks at the interface zone?
Oh, it's a very hard question. Actually, we don't have a software for the material physics, so the researchers must do simulation with another software. We are just provide software for the 3D printing. So by our software, we can just making a tool path and changing a composition while 3D printing. So yeah, you must use another software for the testing an interface between two materials. Okay.
Thank you, Lim. If anyone have any other questions, please contact us on our email or directly to Lim. We will be happy to answer them. And thank you, Lim, for participation in this webinar, for your presentation. I want to tell everybody that the video from this webinar will be available on our YouTube page, Sygnis SA. So please check it in the upcoming week. Again, thank you, and thanks to attendees for being here with us in this troubled times in Europe and the world. So thank you again, and see you on another occasion.